Okay, we're going to solve equations with rational coefficients, and we're going to use our algebra tiles and using that concept of algebra tiles to solve the problem. So the first step, I'm going to draw a line through my equal sign. And remember, our variable is a rectangle. It's our rectangular algebra tile. So I'm going to draw my rectangular algebra tile here, and then I have 12 over here, and I'm just going to use the number 12. Now, I do not need the whole entire x. I only need 3/4 of it. So the 4, which is my denominator, tells me I need 4 pieces. Now, I only need 3/4 of it, so I can cross off one of them. So these 3 parts have to add up to 12. So what number will give me 12? 4 plus 4 plus 4. So 12 divided by 3 is 4. So each one of those is 4. Now my x is the whole rectangle. So that means I would substitute in a 4 here to get the whole entire x. So x would equal 16. I can check this by substituting it into the problem. 3/4 times 16. Turn 16 into a fraction. And when we multiply fractions, we multiply straight across. 3 times 16 is 48. 4 times 1 is 4. 48 divided by 4 is 12, and it checks. Example 2, same idea. I'm going to draw my line through here. I'm going to draw my rectangle to represent my variable, and I have my 10 over here. Now here it says I have 2/5, so that tells me I need 5 pieces. But I only need 2/5 of it, so I'm going to cross off 3 of them. So my t is the whole, what's left is 2/5, and 2/5 has to add up to 10, so that tells me each one of those is equal to 5. I'm going to grab a different color. 5. There we go. Now you can see it. So now the whole thing is my t, which means I have to substitute in 5 for all of these. So t would equal 25. 2/5 of t would be 10. So to check it, I'm going to plug it back in. 2/5 times 25 over 1, so we write it as a fraction, and then we multiply straight across, and I got 50 over 5, which reduces to 10. And it checks. Now number 3 is a little bit different because we have 3 halves. Now thinking about this, 3 halves is the same thing as 1 and 1/2. So I'm going to need not 1 rectangle, but actually 2 rectangles. And each of those rectangles is so each of my rectangles has to be subdivided into halves because it's 3 halves. So I have 1, 2, 3, so I don't need that one. So I have 3 halves of y has to add up to 9. So each one of these would have to equal 9 divided by 3, which is 3. Now the difference is here that I only need 1 rectangle for my y. So if I have 1 rectangle, it would be 3 plus 3, so y would be 6. And I can check my work by doing 3 halves times 6 over 1. That gets me 18 over 2. When I divide 18 by 2 and simplify, I get 9. So it checks. So example 3 is a little bit different because it's 1.5, so it's a whole plus more, where the 1 and 2 were just parts of a whole. So you have to be careful and make sure you're looking to see, do I just have part or do I have 1 and some more? Let's see, I'm going to erase this and we're going to move on to 5 and 6. Scrolling down to 5 and 6. Okay, so 5 and 6, we have, again, a whole and some more. Draw my line. So I have 1 whole x. I'm going to stack them. And then I have 2/3 more. So I'm going to start with the 2/3 more. That tells me I have to divide this up into 3 equal pieces, but I only need 2 of them. Now, this helps me to realize that the one up above, the whole x, that's going to be divided into 3 pieces too, because we want the same denominator. So we have really 1, 2, 3, 4, 5 thirds. So x plus 2/3 is really just 5/3 x. Let me erase that. Now, and again we have 15. So I have 1, 2, 3, 4, 5/3 x has to equal 15. So each of those boxes, those parts, would equal 3. Because 15 divided by 5 is 3. So now again, I need to figure out what is x. Well, x is just one of those. So 3 plus 3 plus 3 is 9. So to check this, I have x is 9 plus 2/3 times 9. And again, we write that as a fraction. 9 plus 2 times 9 is 18 over 3, which becomes 9, plus 18 divided by 3 is 6, and 9 plus 6, fix that, 9 plus 6 does equal 15, so it checks. I'm going to erase the check so that we have room for number 6. Now rewrite that in there. X equals 9. Okay, so we're going to draw my line. So again, we're in the same situation. We have 1 whole x, and then 4/5, I should say y, of 1 plus 1 equals 19. I'm going to go ahead and divide up my variables into fifths. And do your best, understanding that these are all equal in size, even though visually they may not look like it. Alright, so one of them I only need 4/5 of it, so I'm going to cross that off. Now, when we learned in hands-on equations, we can use the subtraction rule of equality that says we can remove the same number from both sides and it does not change my problem. So I'm going to remove this 1, and I just draw a line like this and cross that off, and I'm going to change this to 18 because we took away the 1. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces have to equal 18. So that means each one of those would be 18 divided by 9, which is 2. So each of these would be 2. So my y this time, again, represents one of the rectangles, one whole rectangle. 2, 4, 6, 8, 10. So y would equal 10. Again, to check it, I'm going to plug it in. 10 plus 4/5 times 10 plus 1. I'll go vertically down. So 10 plus, make that a fraction, 4 times 10 is 40, divided by 5, plus 1. 40 divided by 5 is 8, so we have 10, plus 8, plus 1, which is 19. So it checks. Number 7 is a little bit different because we have 2 whole x's, and we want to remove 1/3 of one of those, which tells me that my x's have to be divided into thirds. So if I have 6 pieces and I remove one of them, I'm really left with just 5/3. Plus 2 is 17. So I'm going to remove the 2 from both sides, and I'm left with 15 over here, and I have 1, 2, 3, 4, 5 pieces have to equal 15. 15 divided by 5 is 3. So each of these would equal 3. So my x would equal 1 bar, 1 rectangle, which is 9. So I have 2 times 9 minus 1/3 times, we do 9 over 1, plus 2. 2 times 9 is 18, minus 1 times 9 is 9 over 3 plus 2. 18, 9 divided by 3 is 3, so we have 18 minus 3 plus 2. 18 minus 3 is 15 plus 2, which is 17. Got a little messy there. And it checks. So that is hands-on equations with fractions using the algebra tiles.